Hello and welcome to a quick video showing some notes on Cavalieri and oblique solids with 3D measures. So we're still in geometry, we're still doing 3D measurement with volume type things, but now we're going to look at something where we push around and shift these volumes, but we keep a lot of stuff the same. So the first thing, this is a screenshot, but it's a screenshot of an applet. And I want you to go into the applet, play around with it a little, and then ask or share out here some things that you notice and some things that you wonder. So first, I click on this link. I'm going to open this up in a second tab here. I do need to give it a moment to load. If I need to, I can refresh the page, or I can click down here to refresh as well. I have a couple of check boxes that gives me different views. I have these sliders where I can do some things, and we'll see how those help. And I can also change the location of these dots a little bit. I can move them around. And notice that when I make adjustments to one, it's actually making adjustments to both. I'm going to go ahead and click on this pause button and watch what happens. So what is happening is that this kind of wavy tower is cut into these slabs, but each of those slabs, if I transfer them over and stack them up with kind of a perpendicular vertical line, it becomes just a triangular prism, even if I change this around. So there's this idea of Cavalieri's principle that says as long as these bases or these slabs are consistently shaped all the way through, then you can get the same volume on both. And we notice that here, that it's the same volume. Now I'm going to pause just a moment and kind of reset it. And I'm going to shift the slab. So this is kind of bending those slabs in different ways. So whether it's tilted off to one side or curvy, as long as those slabs still have that same kind of shape, it's equal to the prism, the original prism. Now, let's say that I wanted to show this like with solids. So I can still kind of change that shape into the wavy or like the tilted. Let's do the tilted just for a moment. And this allows me, this slider vertical over here, allows me to show that that triangular base is the same in both 3D figures. In other words, if they have the same height and they have these same slices, then we're going to have equal volumes. It's kind of like we're stacking it off to a little bit to the side, or just kind of counting it here. A real world example of this, let's see if we can find it quickly, is penny stack Cavalieri. Is often this image here. And the idea is that like if you stacked pennies like this, or if you stacked them kind of in a different shape that's not perfectly straight up and down, you're still going to have an equal amount of pennies. I didn't change how much volume or the quantity that I had, but the stack has kind of a different shape to it. All right, so now let's go back to the notes and write some things down that we notice. So I notice that the slabs transfer into a triangular prism. So we have a triangular prism that we could calculate. I also notice that the left shape can be wavy, tilted, or vertical. I wonder, does this work for all prisms? Or what figures does it work for? Now, these are my noticings and my questions. I'm asking you to put something in here that helps make sense for you. What we're going to look at next is a series of examples, and I'm going to show you how to break down, does it fit the criteria that it is a stack that you can calculate the volume for, or does it not fit the criteria? And there's kind of one easy move to do, and we're going to show that in the drawing, and then we'll fill in each of these things. So first, on each of these drawings, go ahead and click on it and then click edit, or you can just double click on there. What I want to determine is, does this base, which is probably rectangular here, does it has to be rectangular. In fact, it's a square base. Does this square base fit this stack all the way up and down, or does it kind of change as it goes? Well, I'm going to use the polyline tool. I'm going to use it kind of like a tracing tool. So I'm going to click on each of these corners, and that's going to create a shape that matches this base shape. There we go. And it doesn't have to be exactly perfect, but you should try to click pretty precise on those corners to do this comparison. Now I notice that this shape is the same down here and on top, so that's great. The top and bottom are the same. But what I also want to check is, what about in the middle, especially in the middle? And do we notice, we'll make this transparent so we can kind of see, does it look like that shape is consistent in the middle as well? It does, which means this is a good stack. Even though it's curved, it has the same base all the way through the top and the bottom, whether we're way down here or if we kind of push it through to the top. It's going to be the same all the way through the top and the bottom. What that means then is I can just calculate this volume as if it were, you don't have to draw the second shape, but as if it were this prism. And we'll flip this to make it look more the same, as if it were just this square prism. Let's see if we can get it to match up there. So we're going to show the height, and there we go. So it's kind of like saying it's going to be the same as this square prism. It's not really square, but it's close enough. And this square prism is 7 by 7 by 10. So how would I calculate that? That's a rectangular prism. Let's look up my volume for rectangular prism. Volume rectangular prism. And it just wants the length, width, and height. Well, my length and width is 7 by 7. And my height, if I go back here, happens to be 10 in the vertical measure. And that gives me a calculation of 490. I'm going to screenshot this little piece here, capture that, and we will say the volume can be determined because all cross sections parallel to the base necessarily have the same area. All right, now let's look at the second one here. This one, we're going to do the same process. I'm going to change to polyline tool, and I'll click on these 4 corners to try and trace this base and see if all cross-section bases are the same or equal. So when let's take that back, undo that. We're going to switch to the arrow tool because now I can drag this base to multiple places. I notice that it fits the top, it fits the bottom, but if I were to line these up in the middle, it doesn't quite fit. Let's put the paint in here again to show this. So it doesn't quite fit. It goes off the edge. It doesn't match up with those corners. It looks like these corners bend in both directions. So if the left side is bending to the right, then the right side should also bend to the right. But it's not doing that. One is bending in to the right, and the other one's bending into the left. So I'll leave that kind of as my cross section that shows that it can't be done. So it cannot be determined because not all cross sections parallel to the base have the same area. So can't be done. On your skill quiz that's related to this, you're going to type in, if the calculation is not possible, you're going to type in the response n/a for not applicable. But you just need to get used to typing n/a. This next one, we have just 6 of these that we're going through, but we're trying to compare when does it work, when doesn't it work. For this one, I can't do the polyline trace, but I do have a circle-like trace. So I'm going to use my circle tool. And then I'm going to try and match this shape as best I can. So there we go. That looks like a good match. And if I kind of push this up the line, I can see that it matches all the way through. So that means that all these cross sections are the same, which also means that it would be the same as a cylinder that has that height of 5 and that radius of 2. So that's what I want to calculate, is the height of 5 and the radius of 2. So I'm going to click Save and Close. And the answer is yes, it can, because all the cross sections have the same area. And the calculation is going to be a cylinder. So we'll type in here volume cylinder. And the radius was 2 and the height was 5. So the radius is 2, the height is, the radius is 2, the height is 5. That gives us this calculation here. Very easy to do. Capture that. Okay, let's do another one. This looks like we have some rectangles in it, kind of like the squares before. I'm going to double click on this drawing to open it up. Because it's rectangular, I'm going to use that polyline tool, click on the corners to trace it out. There we go. I'm going to click on my arrow tool now to move this around. So the top and the bottom are equal. That's good. That's a good sign. But now let's line up these corners kind of somewhere in the middle. And they don't line up with the others. In fact, they're a little short. They should be out there, but that's now where I have to stretch it. That's a middle cross section. Now it's not equal to the top and bottom. So it's not equal. The corners don't line up. So that cross section is not equal. It cannot be determined because not all cross sections are the same area. So again, I will type n/a. It does not work. Let's do another cylinder looking thing. For this one, I'll use my circle shape tool. And I'll try to match this shape as best I can. And that looks good there. Cool. So when I come to the middle, I notice that it has that same width. So that's a good sign. It's matching all the way up and it matches the top. So that means that this cross section is the same and it stacks all the way top to bottom. Because it does that, I can just calculate the volume of a cylinder with a radius 3 and height 8. So it can be done, and all cross sections parallel to the base have the same area. And we got a radius 3, a height 8. So we're going to change these values to 3 and 8 for our volume calculator. We get a new calculation. There we go. So now I have this new calculation with this cylinder. All right, now let's look at this last one here. Double click so we can open this drawing. It is rectangular, so I'm going to use that polyline tool. I click the drop down arrow on the line menu, go to polyline. I'll click on the four corners, reasonably precise. And I notice that the two top and bottom bases match, and if I go somewhere in the middle, I should also see a match for it to work, and it looks like it does. Let's make it transparent to make it even more clean. I can see that I'm hitting all four corners, so it's that same area from the bottom to the top. So because this does work, I can just calculate the area of a box that has this base and this height. So that's a rectangular prism. My length and width is 6 and 5. My height is 6. So my length is 6, my width is 5, and my height is 6. So it calculates to length times width times height. And there's my calculation. Copy and paste it into here. And we should say, yes, it can be determined because all cross sections parallel to the base necessarily have the same area. Excellent. Great, great, great. So that's what we have for these notes. There's more complex versions that you can do where you might have to use a Pythagorean theorem to solve for a vertical height. But just know that you can use Pythagorean theorem sometimes if you have a slanted diagonal height, but you need the vertical height. And that's just a right triangle Pythagorean theorem calculation. And that's it. Thank you.